Alright, so this is lesson 2.10 of our calculus class. Unit 2 is the derivative, and lesson 10 is called the chain rule. So in this lesson we're going to talk about composite functions, which we've talked about in pre-calc. We're just going to refresh our memory of composite functions and how to identify the inner and outer functions. And then we're going to talk about the chain rule, which is what we use when we derive a composite function. So composite functions, a function h, if it's composite, it can be written such that you have function g and function f, where g is inside of f. So you could say h of x is equal to f of g of x. So x would be the input for our g function, and g of x would be the input of our f function. Or we could say g of x is the inner function, f of x is the outer function. So here's some examples. Which ones are composite functions, which ones aren't. The first one is not a composite function, it's a polynomial. We could say it's a function plus a function if we wanted to, but it's not a composite function. Second one, we have a function times a function, but that's not a function in a function. The third one, we have an exponential going on, and the exponent is a variable in it. So we could call this an exponential function, or we can call this a composite function. We could say the inner function is g of x is 3x, and the outer function is e to the power of something function. Okay. The next one is a composite function. We have the inner function is the polynomial x cubed plus 5x, and this inside function is inside of a fourth power function. So we could say f of x, the outer function, is just x to the power of 4. If I put g inside of f of x, then I would get this function. And this is confusing because the example says g of x, and I'm using g of x to represent the inner function, but please know those aren't the same thing. In blue, I'm using g of x to represent the inner function. I should probably change this letter on this example to eliminate that confusion, but now you know. Second one is a composite function. We have an x squared function inside of a sine function. And these two examples that kind of give away that these are composite, is I've got these brackets. And so yeah, that's, if you see brackets, it's probably a composite function. We don't, not all of our composite functions have brackets though, because of our e to the power of 3x example. Okay, the last one, h of x, is not a function. We have 3 times x times e to the power of x. 3x is a function and e to the power of x is a function, but it's not a function inside of a function, so that one's not composite. Alright, so if we identify the inner functions and outer functions, we kind of just did that for most of these on the last slide. The inner function on the first one is x to the power of 3 plus 5x. The inner function on the second one is x squared. The inner function on the third one is 3x. The last one wasn't on the last slide, so let's talk about this one a little more in depth. We have the third root of a 2x plus 1. So 2x plus 1, if we wrote this radical can be written as a polynomial with a rational exponent of 1/3. So you could see the brackets here. We visualize it as a rational exponent. Either way, we have an inside function of 2x plus 1, and then the outer function would be kind of this cubed root function, or this power of 1/3 function. Okay, so here's the chain rule. If I take the derivative of a composite function, it is equal to the derivative of the outer function, where the input, the g of x function side of it, does not change. We just take the derivative of the outside function, so f prime of g of x, and then we multiply that by the derivative of the inside of the function. So f prime of g of x times g prime of x. Let's talk about what that looks like with some examples. So if we take that first one and we derive it, we derive the outside function only first. So Think of this as a power rule. We have the 4 comes in front, and we have the inside function does not change, and the power, for power rule, we subtract 1 from the exponent, so we have 4 times the inside function to the power of 3. And then we multiply this whole thing by the derivative of the inside function. So the derivative of x to the power of 3 plus 5x is 3x squared plus 5. The second example, we take the derivative of the sine function. Derivative of sine is cosine, so we have cosine of the inner function. And then multiply this by the derivative of the inside function. So the derivative of x squared is 2x. Third example, the outside function is e to the power of x. So e is one of those weird functions. We're going to unpack this in a future lesson, but for right now, just know that e to the power of x, the derivative of e to the power of x is just itself, e to the power of x. So if I take the derivative of e to the power of 3x, the outside function doesn't change, e to the power of 3x. And then I multiply it by my inside function. So the inside function 3x, the derivative of that is going to be 3. The last one, the derivative of the outside function, if I think of this as a rational exponent, it's 1/3. I do power rule, so I multiply by 1/3, keep the inside function 2x plus 1 the same, and then I put it to the power of 1/3 minus 1, so negative 2/3. And then I multiply this by the derivative of the inside function. The derivative of 2x plus 1 is just 2. So here we go. Note, I did not simplify any of these. You could simplify some of these, or all of these really, but it's really not that important to me if you simplify them or not. Just to be consistent with the AP test, we're testing your knowledge of calculus, not arithmetic or algebra. So although you will have to do some demonstrate algebra understanding, you don't have to do like the simplifying stuff on this one. Woohoo. Okay, some homework assignment examples. So the derivative of g of x, the inside function is 3x minus 1. So we do 1/2 times 3x minus 1 to the power of 1/2 minus 1. So we get the negative 1/2. And we multiply this by the derivative of the inside function. And the derivative of 3x minus 1 is 3. And so I can write this as a I can turn my negative exponent into a positive exponent in the basement, and I could write it as a radical. I just couldn't help myself, okay? You wouldn't have to simplify this on a quiz, but I just couldn't help myself, so whatever. The second one, we have, well, we could treat this as a quotient rule, but quotient rule is kind of cumbersome. So I'm going to turn this into a function with an exponent that's negative. So just the polynomial to the power of negative 1. And then I'm going to use power rule. Power rule is much simpler. However, this power rule has a function inside of it. So it's not just power rule, it's power and a chain rule. So we'll multiply the 4 by negative 1. That's where we get the negative 4. Times the inside function, doesn't change. And then the inside function gets a power of negative 2. So we just subtract 1 from the previous power. And then we're going to multiply this whole thing by the derivative of the inside function. So the derivative of 2x squared plus 5x plus 3 is 4x plus 5. And then again, I could not help myself. I took that polynomial with a negative exponent and put it in the denominator. And yes, it really bugged me that I didn't multiply this negative 4 through. Because I'm OCD like that. On a homework assignment or a quiz, this is plenty of simplifying. Even the step before that would be plenty simplified. 2 more examples. Another radical example. So we could turn the radical into a exponent, and we could do power rule. And then we notice since we have an inside function of 3x plus 1, we're going to do chain rule as well. So multiply. Once we do the power rule, we'll multiply this whole thing by the derivative of 3x plus 1, which is 3. Second one is kind of the same thing, but because our radical is in the denominator, when I turn it into rational exponent form, the exponent is a negative. And so when we do power rule, we get negative 1/3 times 2, and then this inside function to the power of 1 over 3, negative 1 over 3 minus 1. So that's where we get the negative 4 over 3 from. And then since it's an inside function, we're going to multiply this by the derivative of the inside function. And the derivative of negative x squared plus 8x is going to be negative 2x plus 8. And then again, just like in these example, I just didn't like leaving that negative exponent there. I had to put it in the denominator and write it back in radical form. That's just because I'm OCD. Again, the step before that would be plenty sufficient for a quiz. Takeaways, we can now use the chain rule to find the derivative of composite functions. And so hopefully we get better, as we do some practice, we get better identifying composite functions. A lot of times when we get going on derivatives, we see the power rule easily, but then we can miss that there's an inside function and that we need to multiply by the derivative of the inside function. So don't be that person. Don't forget to do that.